Welcome to Dark Sky Dive, where we explore the deepest complexities of space travel and the engineering marvels of tomorrow. Mars is not just a destination. It is a fortress of solitude guarded by physics, radiation, and immense logistical nightmares.
Many believe that reaching Mars is simply about building a bigger rocket, but the reality is far more complex and dangerous.
Behind every launch lie thousands of solved equations and millions of hours dedicated to overcoming the harsh laws of nature.
The distance between our blue marble and the red planet is a shifting abyss that dictates every single mission parameter.
We cannot simply fly in a straight line because both planets are constantly moving around the sun at different speeds.
For the crew on board, this journey means leaving everything they know behind to face a silence that lasts for months.
Today, we will dissect the technical hurdles, from orbital mechanics to the psychological toll of deep space isolation and survival. We will examine how we plan to protect fragile human bodies from the invisible hail of cosmic radiation. And let us begin with the first major challenge, which is the relentless and unforgiving mathematics of planetary alignment and orbits.
To reach Mars efficiently, we must utilize the Hohmann transfer orbit, an elliptical path that uses the sun's gravity.
This specific alignment only occurs once every 26 months, creating a very strict launch window that we cannot miss.
If technical issues delay the launch by just a few weeks, the mission must be postponed for over 2 years.
Distance varies immensely, meaning the energy required and the travel time can change drastically depending on the launch date. Even with the best alignment, the journey takes 6 to 7 months, a long period of dormancy in deep space.
Engineers speak in terms of delta V, the change in velocity needed to escape Earth and intercept Mars at the right moment.
As the ship accelerates, Earth becomes nothing more than a bright star, a psychological turning point for the crew on board. The vessel must travel at speeds exceeding 25,000 miles per hour just to catch up with the red planet.
Mission planners run thousands of simulations to find the perfect trajectory that balances fuel consumption with travel time and safety.
Throughout this cruise, the spacecraft is exposed to the unadulterated glare of the sun, causing thermal management challenges for systems.
To conquer these distances, we need a vehicle unlike anything ever built before. Enter the SpaceX Starship launch system.
Standing taller than the Saturn V, this fully reusable beast is designed to carry 100 tons of cargo to Mars.
At its heart are the Raptor engines, burning liquid methane and oxygen, a fuel choice specifically made for Martian resources.
Unlike hydrogen, methane is easier to store at manageable temperatures and does not leak as easily through the rocket structure.
The Super Heavy booster lifts the ship out of the atmosphere before separating and returning to the launch tower to land.
Its rapid reusability is the economic key, reducing the cost of access to space by orders of magnitude for humanity.
Once in orbit, the Starship is technically stranded, having used most of its fuel just to escape the gravity well.
Reaching orbit is expensive. The ship arrives with empty tanks, unable to push onward to the red planet immediately.
This brings us to the most critical and risky part of the mission architecture: orbital refueling in the vacuum of space.
Orbital refueling is not just a feature. It is an absolute necessity for sending heavy payloads beyond our home planet.
A tanker ship must launch, chase down the waiting spacecraft, and dock with extreme precision while moving at hypersonic speeds.
Once connected, the challenge shifts to fluid dynamics, as liquids behave very differently in a microgravity environment without weight.
Tons of super-chilled methane and oxygen must be transferred quickly before they boil off due to the sun's heat.
With full tanks, the Starship finally performs the trans-Mars injection burn, leaving the safety of Earth for the unknown. Now begins the long coast phase, where the crew faces threats that no amount of fuel or rocketry can solve.
Deep space is filled with high-energy particles that tear through metal and flesh alike, posing a grave threat to life.
Even more immediate is the threat of a solar particle event, a sudden eruption from the sun, delivering lethal doses. If a solar storm hits, the crew has only minutes or hours to retreat to a shielded shelter inside the ship.
On Earth, our magnetic field protects us. Out here, the hull is the only thing standing between life and death.
Entry, descent, and landing on Mars is known as the 7 minutes of terror. But for Starship, it is even harder. Mars has a terrible atmosphere for landing. It is thick enough to burn you up, but too thin to slow you down.
Parachutes are useless for a ship this heavy. We must rely on supersonic retropropulsion to stop. At the last possible second, the engines must reignite to flip the ship vertical and slow it to a hover.
Survival upon arrival is the next hurdle. They are now on a frozen desert with no breathable air and toxic soil.
We cannot bring enough fuel to return home. We must manufacture it there, using a process called...
Technology can be fixed, but the human mind is fragile. The psychological pressure of Mars is unlike anything else.
Communication is not instant. A simple hello takes up to 24 minutes to travel there and back.
Despite these terrors, the goal remains to build a self-sustaining city, ensuring humanity's survival if Earth faces catastrophe.
Those who go may never return, but their footprints will mark the beginning of our species becoming multi-planetary.
This has been a Dark Sky Dive production. We will see you in the next video. Safe travels, explorers.